Hello student. In the last lecture of the chapter Shear and Bond, we studied the necessity of shear reinforcement in a beam. See, when a beam is subjected to loading, the bending action and shearing actions are there, and both bending action and shearing action produces tension. Due to shear force, there is a diagonal tension, and to resist the diagonal tension, as concrete is weak in taking tension, we have to provide some form of shear reinforcement. The shear reinforcement may be vertical stirrups, inclined stirrups, and bent up bar. Now, to start with the solution of a design of a shear reinforcement problem, step 1 is calculate a nominal shear stress tau v. Tau v is nominal shear stress, which is calculated by force upon area. Here, force is Vu, that is ultimate shear force or design shear force or factored shear force, divided by area of the beam, that is B is width of the beam and small d is effective depth of the beam. Then in second step, we check whether this tau v calculated in step number 1 is not greater than tau c max. Tau c max is maximum shear stress of concrete. That depends upon the grade of concrete, which is given in table number 20 of IS 456-2000. Check that tau v is not greater than tau c max. If tau v is greater than tau c max, we will have to revise the size of the beam. We will have to increase the size of the beam, either B, D, or both, so that tau v is less than tau c max. In no case, tau v should not be greater than tau c max. Then, in step number 3, when it is confirmed that tau v is not greater than tau c max, we will proceed for step number 3, that is calculate tau c considering grade of concrete and PT from the table number 19 of IS 456-2000. Tau c is the actual shear strength of the given beam, and that tau c, if it is greater than tau v, then there is no need of designing shear reinforcement, means actual shear stress coming in the beam, that is nominal shear stress. If it is less than the tau c value, then there is no need of shear reinforcement because the concrete is having capacity to resist that much amount of shear stress, that is nominal shear stress. But IS 456-2000 recommends that to provide minimum stirrups in the form of vertical stirrups having spacing, minimum spacing 0.87 FY ASV upon zero point 0.4 B, whereas ASV is the cross-sectional area of the vertical stirrups. Then, if tau v is greater, means the nominal shear stress, that is the stress due to the external loading, is greater than the capacity of the concrete, then we will have to design shear reinforcement. In that case, we calculate Vs. Vs is the shear force to be taken by shear reinforcement, which is equal to ultimate shear force minus tau CBD. Tau CBD is the shear force taken by concrete, because tau C is the shear stress in concrete, B and D is the area of concrete, B into D. So this gives us the force. This is the force carried by concrete. Shear force carried by concrete. So whatever is the total shear force, ultimate shear force, out of that subtract the shear force carried by concrete, what we will get? Shear force to be carried by shear reinforcement Vs. Now here there is an option. You can provide only vertical stirrups, and second option is stirrups plus bent up bar. Now remember, in no case the shear force taken by bent up bar is greater than 50% of shear force to be carried by shear reinforcement. So it is preferable to provide only syrups. And the spacing of the syrups SV is calculated by the formula 0.87 Fy ASVD upon VUSV, whereas the shear force taken by the bent up bar VUSB is equal to 0.87 Fy ASB into sine alpha. Alpha is the angle at which the bar is bent with respect to horizontal. I will repeat, alpha is the angle made by that bent up bar with horizontal. So using this relation, you can find the shear force taken by bent up bar. Now let us solve some numerical problem. In the first problem, it is mentioned that design the shear reinforcement for a beam 250 mm by 400 mm effective. I will simultaneously write the data given. B 250, B is 250 mm. Effective depth small d is given as 400 mm. The span of the beam, I will consider this as effective span. No, it is given. The span of the beam is 4.25 meter effective. So 4.25 meter effective span. It is L effective. The beam is loaded with a UDL of 12.5 kilonewton per meter. 12.5 kilonewton per meter, including self weight. The beam is reinforced with three bars of 16 mm diameter. So area of steel AST, three bars of 16 mm diameter. So the area of steel is 603.1 mm square. This is the area of steel. Fe415, Fe415 and M20 are used. And what is required? Design the shear reinforcement. Now let us start with the solution. First of all, what I will do, I will find the factored load, because the given load, it is not mentioned that it is safe load or factored load. So factored load WU is equal to 1.5, which is the partial safety factor for load, into the given load 12.5 kilonewton per meter. So it is 18.75 kilonewton per meter. This is factored load. After finding the factored load, I will find the factored shear force VU, which is WU into L effective divided by 2. See, this is the formula which we studied in mechanics of structure when the beam is subjected to UDL. Suppose this is WU factored UDL. This is L effective. Now the reaction at A, due to symmetry, reaction at A will be equal to reaction at B, which is equal to total load, that is WU into L effective is the total load divided by 2. Half of the load will be taken by RA and half of the load will be taken by RB. So WU is 18.75, L effective is 4.25 divided by 2. So I will get the factored shear force 39.84 kilonewton, say 40 kilonewton. So factored shear force is 40 kilonewton. Now, as the area of steel is given, I can find PT. PT is AST upon BD into 100. that is equal to, why it is required? To find the tau C for in the next step. So PT is AST upon BD into 100. So AST 603.1 divided by B. B is given as 250 and D is 400. So I got the percentage of steel as 0.6%. 0.60%. Now, let us start with our step. Now, this is the data which was given. I have converted to our requirement. Now, step number one, tau V, which is the nominal shear stress, VU upon BD. VU is 40 into 10 raised to 3, that is in Newton, divided by the area is B is 250 and D is 400. So this is equal to zero point 0.4 Newton per mm square. So we got tau V. This is step number one. In step number two, we check whether the tau V is not greater than tau C max. So tau C max for the grade of concrete is given as M20. Grade of concrete is given as M20. So for M20 we will find the tau C max. For M20 we will find the tau C max from table number 20. See, this is the table number 20. See, for table from table number 20, for M20 grade concrete, the tau C max value is 2.8. So tau C max is equal to 2.8 Newton per mm square for M20 grade concrete. This is from table number 20. Check whether this tau V is not greater than, tau V is not greater than tau C max. Tau V is zero point 0.4, is not greater than 2.8, so it is okay. Now, in the step number 3, next step, find tau C. Tau C depends upon grade of concrete and PT, percentage of steel. This is given in table number 19 of I score. Now, referring to that table, what I will write? PT, value of PT and tau C. For PT equal to 0.5 and tau C is 0.48, and for PT equal to 0.75, tau C value is 0.56. Why these two values are taken? Because the PT, percentage of steel, is 0.6. So I must consider value of PT below 0.6, that is 0.5, and above 0.6. So 0.6% is in between this. So therefore I am considering these two values of PT 0.5 and 0.75 and corresponding values of tau C, that is 0.48 and 0.56. Now by interpolation I will find the value of tau C for PT equal to 0.6%. By interpolation, I will calculate 0.48 plus into bracket 0.56 minus 0.48 divided by 0.75 minus 0.5 into 0.6 minus 0.5. This is by interpolation. I am finding the value of tau c for the given PT, that is 0.6%, and after calculation I got 0.512 Newton per mm square. So this is the required tau c value for PT 0.6 by interpolation. Now I will compare this tau c value with tau v. Now tau v is 0.4. So as tau v is less than tau c. See, tau v is 0.4 is less than tau c is 0.51. It means whatever is the shear stress coming in the beam, that is due to external loading, is zero point 0.4 Newton per mm square, whereas the concrete has capacity to resist 0.51 with the given AST and grade of concrete. So concrete is able to resist this shear force. No need of shear reinforcement. No need of shear reinforcement. Why? Because whatever is the shear stress, nominal shear stress coming in the beam, that is 0.4, is less than the capacity of the concrete with the given percentage of steel, and considering the grade of concrete is 0.51. So capacity of concrete to resist the shear stress is 0.51, whereas the actual shear stress coming in the beam is 0.4. No need of shear reinforcement. Concrete is able to resist that shear stress, but IS code does not allow this. It recommends to provide minimum shear reinforcement. Minimum shear reinforcement. And that is in the form of minimum shear reinforcement is in the form of SV minimum. We can write SV minimum. That is the spacing of stirrups is equal to 0.87 Fy ASV upon zero point 0.4 B. Now here let us consider 6 mm diameter mild steel, that means Fe250, Fe250 two-legged two-legged vertical stirrups. See, two-legged vertical stirrups means the area of stirrups. In calculating the area of stirrup, that is ASV, what I will do, ASV equal to 2. This 2 is for two-legged, pi by 4 d square. This is the area of stirrups, and that is equal to 56.4 mm square. Let me check. 56.52. 56.52 mm square. So 0.87 Fy, I am assuming my steel for stirrups, 56.5 divided by zero point 0.4 into B is given as 250. So simplifying this, what I will get 122.9 mm. Always round it to lower side, say 120 mm. So spacing, minimum spacing I got 120 mm. Now check for maximum spacing. I will check this for maximum spacing because there is another clause given by IS code. The spacing should not be greater than 0.75D and it should not be greater than 300 mm, whichever is less. Now 0.75D means 0.75D is, what is the value of D? Let me check. What is the value of D given? Value of D given as 400 mm. So 0.75 into 400 into 400, that is 300 mm. Now we got three values of spacing, means according to this clause spacing should not be greater than 300 mm. This is one. Spacing required considering the minimum shear reinforcement clause is 120 mm. So always minimum of all the values after considering all the clauses given by IS code. So final answer is provide 6 mm diameter, two-legged vertical stirrups at a distance 120 mm center to center. This is the final answer. Now here one can adopt 8 mm diameter torque steel stirrup. So let me calculate. See, this is another solution, or I can write or here. If one assume that providing if 8 mm diameter tor, see this is the sign of tor, Fe415, see tor steel means either Fe415 or Fe500. So if 8 mm tor Fe415, two-legged stirrups are assumed, then SV minimum is equal to 0.87 Fy, 0.87 Fy ASV upon zero point 0.4 B. Here ASV is equal to 2 into pi by 4 8 square, and Fy, as I am assuming Fe415 is 415 Newton per mm square. So 0.87, substitute the values of this Fi415 and ASV, 2 into pi by 4 8 square, B is 250, what I will get, SV is 362.9 mm, say 360 mm. So SV minimum I got 360 mm, 360 mm. But according to the another clause, that is spacing should not be greater than 0.75 D. In this case, D is 400. So 0.75 into 400, that is 300 mm, and it should not be greater than 300 mm, another criteria. So according to this, spacing should not be greater than 300 mm, and according to the spacing, minimum spacing, considering the minimum shear reinforcement criteria, it is 360 mm. So just I told you, finalize the minimum of the two values considering the all the criterias for spacing. So in this case, the final answer is provide 8 mm torque, two-legged vertical stirrups at 300 mm center to center. Minimum of all the values that is calculated considering the all the criteria given by IS code, you will finalize minimum of the all values. So this is the solution of design of shear reinforcement for the given problem. Thank you.